Okay, assalamu alaikum. Let's begin. So we're doing limits of accuracy today. It's a short topic. It's not going to take that much time. Let's start with this. So what is this about? Well, in this topic, we basically talk about lower bounds of different things, upper bounds of different things. Let's take an example. Let's say you have a rectangle that looks like this. Okay, and you know the length of this rectangle, and you have the width of this rectangle, and let's say you're measuring this length and width using some scale, and you figure out that the length of this rectangle is 8 centimeters, and the width of this rectangle is, let's say, 5 centimeters, or let's say it is 3 centimeters. Length is 8 centimeters and width is 3 centimeters. We have a rectangle like this. Now, the catch is that you are basically measuring the length and width of the rectangle with something that cannot measure this very accurately. Okay, so it has uh, marks at an interval such that it's not possible to measure the length very accurately. And based on the measurement tool that you've got, you can only say that the length 8 centimeters, this is correct to a certain level of accuracy. So let me write that down here. So let's say we've got this rectangle. The length of this rectangle, the length of the rectangle is 8 centimeters correct to the nearest centimeter. And the width of the rectangle is 3 centimeters. Again, you're using the same measuring tool for this as well. So the width is 3 centimeters correct to the nearest centimeter as well. Now, what you want to do is you want to find the maximum possible length of this rectangle, the maximum possible width of the rectangle, the minimum possible length of the rectangle, the minimum possible width of the rectangle. So 8 centimeters is correct to the nearest centimeter. Now, what exactly does this statement mean? Correct to the nearest centimeter. This nearest centimeter, this is basically the accuracy level for your measurement. So if we write that down here, the accuracy level of this measurement that they've given is nearest 1 centimeter. Right? Nearest centimeter means they're saying it's nearest 1 centimeter. So the accuracy level is to the nearest 1 centimeter. That means we know for sure that if we round off the actual length, it turns out to be 8 centimeter and not 7 and not 9. To the nearest 1 centimeters, it is supposed to be 8 centimeters. For example, if the actual length was, for instance, 7.8, that rounds off to 8 centimeters, right? So even if the actual length was 7.8, using the measurement tool that we've got, what we're saying is that correct to 1 centimeter, this is going to be 8 centimeter. On the other hand, if you had some other length, for example, 6.3, what would that round off to? 6.3 would round off to 6. If you had uh, if you had 7.4, that would round off to 7. So what values are going to round off to 8? What possible values can round off to 8? Basically, any value that is between 7.5 and 8.5, that is going to round off to this number 8. That's what it means that to the nearest 1 centimeter, the length of the rectangle is 8 centimeters. That if the actual length, if the length that we're calculating is 8 centimeters, then the actual length could be anywhere between 7.5 and 8.5, right? Because that rounds off to 8 centimeters if you rounded off to 1 centimeter. Okay. Now, what does that mean? The number that we've got here, that the length is 8 centimeters, there's a possible error in this number, right? It's rounded off to the nearest centimeter. What that means is this 8 centimeter number, the actual number, the actual length of the rectangle could be anywhere between 7.5 and 8.5. In other words, we have an error that is possible in this length, and that error is basically of 0.5 on either side. So from 8, you could go minus 0.5 to the left side and plus 0.5 to the right side. So that gives you these these possible values for the actual length. The actual value could be anywhere between 7.5 and 8. This number, the maximum possible difference from 8 centimeters that we can have for the actual length, we say this is the error that is possible in this measurement. So 8 centimeters, the length that we are getting from that, it actually could be anywhere between 7.5 and 8.5. Why? Because we could have 0.5 error on either side of 8 centimeters. This is the error that we could have in that measurement. Whenever you have any accuracy level given in the question, an accuracy level given for any measurement, you can find the possible error from that like this. You would say it's equal to the accuracy level. The accuracy level is 1 centimeters divided by 2. So in this case, you can say the accuracy level would be 1. So 1 divided by 2, the possible error is 0.5. 0.5 on either side of this number 8, right? So the actual value for the length, it could be between 7.5 and 8.5. And similarly for the width as well, since that is also correct to the nearest centimeter, the actual width is also going to be somewhere between 2.5 and 3.5, because that is what we get when we do 3 plus minus 0.5. 3 plus 0.5 will give us the maximum possible width, and 3 minus 0.5 would give us the minimum possible width in this case. Now, that's basically the idea of limits of accuracy in upper bound and lower bound, that for any measurement that we have, for which there is some error possible, whatever level of accuracy that you're given, you can find the possible error in that measurement by dividing that accuracy level by 2 like this. And then you say your actual values of whatever that number is, they could be within a set of numbers, which basically is going to come from this possible error. So if the length is, for example, 8 centimeters, you could say the actual length could be anywhere between 8 minus 0.5 and 8 plus 0.5, it will be 8 plus minus 0.5. And the actual width would be anywhere between 3 plus 0.5 or 3 minus 0.5. So if I were to show that, if I were to copy that rectangle here again, and now based on that understanding, if you were told that this is a rectangle and you're measuring the length and width of this rectangle using a tool that can give you a number correct to an accuracy level of 1 centimeters to the nearest 1 centimeters, what would be the upper bound? What would be the upper bound of the length of the rectangle? The maximum possible length of the rectangle. How can you find that? You would say it's being measured correct to 1 centimeters. So you would find the possible error in this, first of all, the maximum possible error that you can have. That's going to be 1 over 2 in this case. That's 0.5. The maximum possible error is 0.5 in this case. That means the upper bound for this length, the maximum possible value of length could be 8 plus 0.5, which is 8.5. The lower bound for the length, lower bound of the length of the rectangle, lower bound of the length of the rectangle, what would that be? That would be 8 minus 0.5, which turns out to be 7.5. And similarly, we could find the upper bound and lower bound for the width as well. We would say the upper bound for the width in this case it also has the same level of accuracy, right, to the nearest 1 centimeter. So the possible error that you could have in this case as well is going to be 0.5. So you would say the measured length, the measured width is 3 centimeters. The maximum possible width could be 3 plus 0.5. That's 3.5. And the minimum possible would also be 3 minus 0.5. And that gives you 2.5. Where does that come from? Any number between 2.5 and 3.5, you know, that is going to round off to 3. So if the width is being measured as 3 centimeters to the nearest 1 centimeter, then the actual length could be anywhere between this. This is the idea of upper bound and lower bound. Okay, this is how we calculate upper bound and lower bound for any number. Now, in this case, we were given that the measurement is correct to 1 centimeter, right? Correct to the nearest centimeter. What if we were to change it slightly now and we were given something else? And that will make it clearer now. Instead of centimeters, let's say we had something else. So let's say we had some big area, big town, let's say, and it's in the form of a rectangle. It's a rectangular shape, right? It's a big town. And it's so big that it's in kilometers, that one side is maybe, let's say, this is, or let's consider a big city instead of this, or a big province. And let's say that's in the form of a rectangle. And let's say one side of this is maybe 75 kilometers. And then the other side is maybe 30 kilometers. And what you're doing is, you're saying the length of this rectangle is 75 kilometers, correct to the nearest 5 kilometers. And the width is 30 kilometers, correct to the nearest 5 kilometers. Given this, what is the maximum possible length of this rectangle and what is the minimum possible length of the rectangle? Now, this is the formula that we're going to remember for this. The maximum possible error, what is that given by? Maximum possible error in a measurement, that is going to be the accuracy level divided by 2, okay? Accuracy level divided by 2, that is going to give us the maximum possible error in any measurement. So in this case, what's the accuracy level that is given? The accuracy level that's given is 5 kilometers, right? It's correct to the nearest 5 kilometers. You would say the error that is possible on either side of these numbers is going to be 5 divided by 2, and that's 2.5 kilometers. So if we have to find the upper bound of the rectangle, the lower bound of the rectangle, of the length, upper bound of the length, and similarly upper bound of the width and the lower bound of the width, how could we find that in this particular case? We could say the upper bound of the length of this rectangle is 75 plus 2.5, right? So we could have an error of 2.5 on the upper side. So maximum we could get to would be 77.5. And the minimum we could have here in this case could be 75 minus 2.5, and that would be 72.5. Okay. And for the width, this is 30. We could say that's 30 plus 2.5, and that gives us 32.5. And the minimum possible width, what would that be? 30 minus 2.5, and that's 27.5. This is how we find lower bound and upper bound of anything. We find the maximum possible error, and then we say whatever is the quantity that we're given, we could say that plus the error, that gives us the upper bound, and that minus the error, that gives us the lower bound. Okay. So in the first case, it's 75 plus minus the error. That's giving us the maximum and minimum possible values. In this case, we're doing 30 plus minus the error. That's giving us the maximum possible and the minimum possible dimensions of this rectangle. Okay. Now, these were simple cases in which we just had the lengths and widths, and we had to find their upper and lower bounds. But what if you had to find the maximum possible area in this case? So what if they asked you for the maximum possible area of the rectangle? What would that be in this case? Maximum possible area. Now, what is maximum possible area going to be? Let's first of all find out, let's first of all write down the formula for the area of rectangle. What's that? Area of rectangle is given by length into width, right? That's the area of a rectangle, length into width. We want to find the maximum possible area given that the length is 75 kilometers, the width is 30 kilometers. Now, what does that mean? The length could be, since it has a possible error, it's correct to the nearest 5 kilometers. We know that the length is actually going to be anywhere between 72.5 and 77.5. So we have a possible error of 2.5. Okay. And the width also, it can be anywhere between 27.5 and 32.5. That means it also has a possible error of 2.5. If we want to find the maximum possible area, these two things are multiplying. We are multiplying length and the width. If we want to maximize the area, we would want to have the maximum possible length for that. And we would also want to have the maximum possible width for that, right? The higher the length is, the higher the area is going to be. And the higher the width is, the higher the area is going to be as well. So the length and width, we want them to be as big as possible. What's the maximum possible length that we've got? That's the upper bound of the length, right? 77.5. So we use this one, 75 plus 2.5. In this case, that's 77.5 times the maximum possible width, that's 30 plus 2.5, which is 32.5. You multiply these two numbers, and that's going to give you the maximum possible area of this rectangle. You can see what that turns out to be, 77.5 times 32.5, and that's giving me 2518.75. That's the maximum possible area we could have in this case. Now, this is how you would approach problems like these. If you want to find some quantity that is not already given, and you have to find that by calculation, you first of all write down the formula for that, and you try to think of, if you want to maximize this, what would you want each of these quantities to be? So if you want to have the maximum possible value of area, the length would have to be maximum and the width would also have to be maximum in this case. Okay. So we use the maximum and maximum possible values for both of them. Now, a wrong way of doing this would be, which a lot of people end up doing in the exam, that what they would do would be they would say, let's find the area of the rectangle. The area of the rectangle using the original numbers that are there, which are 75 and 30. You multiply them. That gives you 75 into 30, and that is 2250. And then they say, since the accuracy level is 5 kilometers, the maximum possible area, we say, let's add 2.5 to it, and that gives us 2252.5. This is not the correct way to approach this. The accuracy level that was given was not for the area of the rectangle. The accuracy level that we were given, that was basically for the length and the width. We can't find the area first and then add 2.5 to that. We would first have to find the maximum possible length and then find the maximum possible width, and use those maximum possible values of length and width to find the maximum possible area like this. So the actual maximum area, it turns out to be 2518.75. This can also be called the upper bound of the area, right? So upper bound means the maximum possible value of something. Lower bound means the least possible value of something. So this is the upper bound of the area, 2518.75. Similarly, if you wanted to find the lower bound, you would use the least possible value of length and the least possible value of width. Okay, let's take another example. Let's say we had something like this. A car is traveling at a speed of 'or you can say a car covers a distance of 300 kilometers in 4 hours. Now, the distance that we have here, that is measured correct to the nearest ten kilometers, and the time is measured correct to the nearest tenth of an hour. Okay, now how do we think about this? We've got the distance value, that's 300 kilometers, and we have the time value, that's 4 hours. What we need to do is we need to find the maximum possible value for this average speed of the car. For the average speed of the car. This is the information that we're given, that the car is traveling a distance of 300 kilometers in 4 hours. Distance is correct to the nearest 10 kilometers. 300 to the nearest 10 kilometers. 4 hours to the nearest tenth of an hour. We need to find the average speed of the car. Now, these are some terminologies that are important to remember. It says nearest tenth. Now, what exactly does that mean? Tenth means 1 over 10, okay, which is 0.1. So, 10 means 10, right? 10th means 1 over 10. Similarly, 100 is 100. If they say 100th, something is measured correct to the nearest 100th, what would that mean? That would mean 1 over 100. Okay, and that is 0.01. Similarly, 1000th and so on. So if 10 is 10, 10th is 1 over 10. So when they say it's correct to the nearest 10th of an hour, that means to the nearest 0.1 hour. That's the accuracy level for time that we're given. So what can we say about the distance now? Distance is 300, right? What about the actual value of the distance? What could that be? It could be plus minus the maximum possible error. What's the possible error in this case? The error is, it says 10 kilometers. It's measured correct to the nearest 10 kilometers. You would say it's 300 plus minus 10 over 2, or 300 plus minus 5. So the actual distance is anywhere between 295 and 305. And similarly, the actual value for time that we have there, what is that? That's 4 plus 10th means 0.1. So it's 4 plus 0.1 divided by 2, or we can say 4 plus minus that, 4 plus minus 0.05. So the time could be anywhere from 3.95 to 4.05. So distance is for anywhere from 295 to 305. You see all values in this interval, they would round off to 300, right? And time is anywhere between these two values. And again, you can see numbers between 3.95 and 4.05, they would round off to 4. These are the maximum and minimum possible values for distance and time. What were we looking for? We were looking for the maximum possible value for the average speed of the car. What is speed given by? Average speed formula is its distance over time, right? Speed is calculated as distance over time. If we want to maximize speed, we want the maximum possible value for speed. Now think about it. We have a fraction here. If you have a fraction a over b, when would this fraction be big? If the numerator is as big as possible and the denominator is as small as possible. Let's take an example. So let's say you have 5 over, or let's fix one of them first. So let's say the denominator is 5. Now, if one fraction has a numerator 6 and another fraction has a numerator of 13, which one is bigger? The one that has a bigger numerator. So numerator being big means that the fraction is bigger. And if we fix the numerator and we say the numerator is, let's say, 5, and we have 5 over something here, 5 over something here. If we have 5 over 2 as compared to 5 over 7, which one of them is bigger? When the denominator is smaller, the overall number is bigger. When the denominator is bigger, the overall number is smaller. So this is a bigger number and this is a smaller number. Why? Because in one of them, denominator is smaller. When the denominator is small, the overall fraction is big. When the denominator is big, the overall fraction is small. So if we want to maximize speed, if we want the maximum possible value of speed, what does that mean? We would want the numerator to be as big as possible. So numerator needs to be big in this case. And we want the denominator to be as small as possible. So time needs to be as small as possible. So what would be the maximum speed in this case then? Maximum possible value for distance is 305. So we use that from there. The minimum possible value of time, that is 3.95, we use that number from there. And we say the maximum possible speed is going to be given by this 305 divided by 3.95. And that gives us 77.2 kilometers per hour. This is the maximum possible average speed we could have in this case. Okay, we don't say distance and time, both of them are going to be maximum in this case. No, if we want to maximize the overall expression, we want the denominator to be as small as possible. Okay, similarly, if in this case we wanted to find the minimum possible value of speed, even though they've not asked about that in this question, but if we had to find that, again, the formula is distance over time. If we want the minimum possible value of speed, we would want the numerator to be as small as possible and the denominator to be as big as possible. So what's the smallest possible value of distance? That's 295. The largest possible value of time, that's 4.05. And that is going to give you the minimum possible value of speed in this case. That's 295 divided by 4.05. And that is 72.8 kilometers per hour. That's the minimum possible speed that we could have given this scenario. All right. Now let's generalize it. How would you deal with problems like these if you have anything like this? If you had, for instance, any quantity A, and this was calculated like this: B plus C or B minus C, or let's actually keep to B plus C, and then B minus C, B minus C. And what we want to do is, we want to first find the maximum possible value of A and the minimum possible value of A. The maximum possible value of A, minimum possible value of A. Similarly, we could have something defined like this: A equals B times C. These are common cases that you would see, right? When you have addition, subtraction, multiplication, or division. Or you could have A equal to B over C. In this case as well, we want to find the maximum A or the minimum A. Maximum A or the minimum A. Okay. Now, if we had a quantity that's A equal to B plus C, if we want to maximize that quantity, what would be the maximum possible value of A? How would we maximize A? We would have to maximize both B and C. We would need the maximum possible value of B and the maximum possible value of C, and that is going to give us the maximum possible value of A. If we want the minimum possible value of A, in that case, since we're adding these two numbers, we would say we want the minimum possible value of B and the minimum possible value of C. If both numbers are small, their sum is also going to be small. Okay, so we would want both the numbers to be as small as possible. In the second case, if you have A defined like this, A equal to B minus C, if we want to maximize A, how can we maximize A in this case? If you want to maximize A, it's B minus C. The positive number, we would want that to be as big as possible. If you want the maximum possible value of A. And then the negative number, the one that we are subtracting, that would need to be as small as possible. Then the overall result would be something big. Similarly, if you're looking for the minimum possible value of A, we would want the positive number to be as small as possible and the negative number to be as big as possible, right? We would want this number to be small and this number to be big. So for example, if you're subtracting one thing from another thing, if you have 5 here and let's say 1 here, that gives us 4. But if we make this number small, so this number is, let's say, 2, and this number becomes bigger, you see what happens to the overall result? It becomes smaller. So this number becomes smaller and this number becomes bigger. The overall result becomes smaller. So if we want the overall result to be small, we would want this number to be as small as possible and this number to be as big as possible. Similarly, when we are doing multiplication, in multiplication, if you want the maximum value, you would want both numbers to be as big as possible, because the larger the numbers are, the larger their product is going to be. If you want the minimum possible value, in that case, you would want both the numbers to be as small as possible. So in addition and multiplication, whatever is that you have on the left side, if you want to maximize this, you would have to maximize the quantities on the right side of the formula as well. But in subtraction and division, it works the other way. If you want the maximum value of A now, that is defined as B over C, in order to maximize this whole thing, you would want the numerator to be as big as possible, and you would want the denominator to be as small as possible. So denominator would be as small as possible. Okay. If you want the minimum possible value of A, in that case, you would want the numerator to be as small as possible and the denominator to be as big as possible. Okay, so for minimum value, we would want to minimize the numerator and maximize the denominator. Okay, so what do you need to remember about this? Error is calculated like this: accuracy level divided by 2. Okay, keep that in mind. Understand what 10th, 100th terminologies like these mean. And then if you have to find lower bound or upper bound of something, you just say that original number plus minus the error. Original number plus minus the error. And if it's some quantity that you have to calculate, first of all, like for example, you're given information about distance and time, and you want to find speed, you think about the formula for that, and then you see which quantity you have to maximize, which quantity you have to minimize based on these rules that we've discussed. When we're adding or multiplying, what we do is we want to maximize and minimize those numbers as they are. For example, if you want to maximize the whole quantity, we want the individual numbers to be maximum. If we want to minimize the whole quantity, we want the individual numbers to be minimum. But for subtraction and division, the first number has to be, so if you want to maximize something, the first number has to be maximized and the second number has to be minimized. Here as well, if you want to maximize something, this number has to be maximized, this number has to be minimized. And for the minimum possible value of something, it will be the other way around. Okay? All right, now that's the idea. Let's have a look at some questions now to see how this is tested. Now, this is from the non-calculator paper, first of all. Let's have a look at this. It says Mariam's height is 1.52, correct, to the nearest centimeter. Nearest centimeter, what does that mean? To the nearest 1 centimeter. That's the accuracy level that you're given in the question, right? That's the accuracy level. Now, given that accuracy level, we know the error is going to be half of that, right? State the lower bound of her height. Now, height is 1.52. We want the lower bound, so we say let's subtract the possible error in the measurement, 1 divided by 2. So let me write down the error here first. The error is going to be 1 over 2, right? That's 0.5. So we say minus 1 over 2, or 0.5. That is going to give us 1.4. Okay, I'm sorry, this is meters and this is centimeters. So you have to first convert it to the same unit first of all. So the error is 0.5 centimeters. Okay. Now you can either work with meters for both of them, or you can work with centimeters for both of them. It's easier to work with centimeter first. Otherwise, it will be too many decimal places. So let's convert this to centimeter first. 1.52 meters. What's that in centimeters? That's 152 centimeters. So that will become 152. For the lower bound, we subtract 0.5, and that gives us 151.5 centimeters. Now you convert that to meters, shift the decimal place 2 units to the left, or just divide it by 100, right? So that will give you 1.515 meters. That's the lower bound of the height, 1.515 meters. You should give the answer in the same unit that they used in the question. Do not convert it to centimeters for the final answer. The final answer has to be in meters. Now it says the length of each of Miriam's paces is 0.55 meters. She walks at a constant speed of 2 paces per second. Calculate the distance that she walks in 1 hour. Okay, now that's not something that requires limits of accuracy as such. We've got the length of of 1 pace. She is walking at a speed of 2 paces per second. The distance in kilometers that she walks in an hour. How can we calculate that? We know the total time, that is in hours. Now there's too many units that we have here. 0.55 meters, that's the length of 1 pace. What's 2 paces? 2 times this. So in every second, what she is doing is she is traveling 0.55 to 0.55 times 2, which gives you 1.1 meter per second. That's the speed that we're given, right? 2 paces per second, that means 2 into 0.55, that's 1.1 meters per second. That's the speed that we've got. We want to find the distance in kilometers. Okay, distance in kilometers that she travels in 1 hour. Now, the speed has seconds here. Let's convert the speed to kilometers per hour, first of all. How can we do that? 1.1 meter per second. How do you convert meter to kilometers? How do you convert meter to kilometers? 1 kilometer has 1,000 meters. So if you want to convert this to kilometers, you would multiply, or you can say it's 10 raised to power 3 meters. If you want to convert it to kilometers, you have to multiply it by 10 raised to power minus 3. For seconds, if you want to convert it to hours, how do you do that? 1 hour, what is that equal to? That's equal to 60 minutes. And then each minute has 60 seconds. So that's 60 times 60, 3,600 seconds. Okay. Now that basically gives you that 1 second is 1 over 3,600 hours. So for this, we can say, let's multiply this by 1 over 3,600. In the numerator as well, if you wanted, you could write it like this. You could say this is 1 over 1,000. Okay, and now you'll simplify this, that will convert to kilometers per hour. Now, some of you might find it easier if I write it like this. So you can write it like this first. You can say this is 1.1 meters per second. So you can say meters per second, write it separately like this. If you want to convert this to kilometers here, how do you go from meter to kilometer? You basically divide this by 1,000. And then how do you convert seconds to hours? You can divide this by 3,600. And now this becomes 1.1 into 1 over 1,000 into 3,600. And you can see what that turns out to be. This will be in kilometers per hour. That's the speed that you've got. This becomes 1.1 into, this gets cancelled. 36 over 10, that is 3.6. Okay, now keep it as it is for now. This is the speed that you've got in kilometers per hour. What are we looking for? We're looking for the distance traveled in 1 hour. So you just multiply it by 1 and that will give you the distance. How do you do this multiplication? Now 1.1 into 3.6. You can do this multiplication. On the side here, 1.1 is the same thing as 11 over 10. Into 3.6 over 10, that's 36 over 10. And that gives you 36 times 11, that is 396. 360 is 36 times 10 plus 36, that's 396 divided by 100, that's 3.96. So this basically ends up being 3.96 kilometers per hour. Multiply this by time, which is just 1 hour, and you would get the distance that's 3.96 kilometers. Okay, now that did not involve any limits of accuracy. Let's have a look at another one that does require us to use that. Let's do one that is relatively more complicated. So let's have a look at this. In a race, an athlete runs 1600 meters at an average speed of 6 meters per second. The distance is given correct to the nearest 100 meters and the speed correct to the nearest meter per second. Okay, now how do we think about this? 1600 meters, that's the distance. What's the level of accuracy? The level of accuracy is nearest 100. So it's going to be plus minus 100 over 2. That gives you 1600 plus minus 50. It's just complete these statements in the answer space. Distance is going to be between these two numbers, 16 minus 50 and 16 plus 50. What is 16 minus 50? That's 1550. So the least possible value of distance is 1550. The maximum possible value of distance, 1600 plus 50, that would be 1650. So the actual distance is anywhere between 1550 and 1650. Okay, then it says, the speed is given correct to the nearest meter per second, to the nearest 1 meter per second, right? So you can say this is 6 plus minus 1 over 2, right? Plus minus 0.5, that means 6 plus minus 0.5. So speed is going to be between 5.5 and 6.5. Now it says find the greatest possible time the race could have taken. What's time equal to? Speed is equal to distance over time, so time is equal to distance over speed. If we want to find the greatest possible time, the maximum possible time, what do we want the numerator to be? We want the numerator to be as big as possible and the denominator to be as small as possible. So what's the numerator going to be? The maximum possible value of distance, that's 1650. Denominator, the smallest possible value of speed, that's 5.5, and that should give you the result. This is from a non-calculator paper, so we'll have to do this manually. 1650 over 5.5. Let's have a look at the units. It's seconds, meters, and meter per second. Okay, so the unit is fine. We have to calculate this now in seconds. Okay, so what do we do about this? We can say it becomes 1600 divided by 5.5, or that's the same thing as 1600 multiplied divided by 55 over 10. Okay, you can do this in multiplication form now. It becomes 16,000 divided by 55. You've got to do this division now. It doesn't look like we have a quick way of doing this, so we would have to do long division for this. Are we sure it's from the non-calculator paper? Okay, anyway, if you have to do this manually, how to do that? Let's do the division. 16,000 divided by 55. Let's see what we get from this. Okay, 160, 55 multiplied by 2, that gives us 110 here. You are left with 500 from this. 55 times 9, that is going to give you 495, because 55 times 10 is 550, and 55 times 9 then would be 495, and that leaves me with 9 there. Let's subtract this, and that gives me 5, and I have 50 here. That is not divided. 5 times that is going to be We cannot do that, so we have another 0 here. Why is this becoming so long? Here's what's what time today it's gonna have taken. Okay, 55. What if we multiply this by now 495, and that will give you 5 here. So again, you add another decimal here. It looks like, let's check this again. Is this from a calculator paper? So one more question. Okay. Okay, so what we can do is we can actually just stop at this point now, because we just add another 2 zeros now. And that actually gives us, already, in fact, we have 290.9 here. So we can stop at this point. So we don't have to do the complete division. So in that case, that's all right, because we can stop at this point now, since the answers are supposed to be given to the 3 significant figures level of accuracy. We can have that here already now. We've got 290.9, so we can say this is 291. That's the number of seconds that we would have in this case. For this raised to 3 significant figures, it becomes 291. Okay, so we can run it off like that. Okay, let's have a look at another one. Okay, let's try this. A rectangular box has dimensions 30 centimeters by 10 centimeters by 5 centimeters. A container holds exactly 100 of these boxes. Calculate the total volume of the 100 boxes. Okay, so we have a rectangular box that's given by this 30 times 10 times 5, and that's 300 times 5, and that gives us 1500 centimeter cube, right? When we multiply these three numbers, 300 times 5, that's 1500. But then we have 100 of these boxes. This is for one box. We multiply this by 100, and that gives us 150,000. That's in centimeter cube, but we want it in meter cube. What we do for that is 1 centimeter, 1 meter has 100 centimeters. So we divide it by 100 cube. How many zeros is that going to be? 6 zeros in the denominator. 15, and then 4 zeros divided by 1 0 0 0 0 0 0, and then we have 0.15 from that. 1 2 3 4 5 6. Yeah, so 0.15 meter cube. That's the volume that we've got in this case. Now it says each box has a mass of 1.5 kilograms to the nearest of 0.1 kg. So we've got the mass given. It's 1.5 plus minus, so this is 0.1, right? Divided by 2, what does that become? It becomes plus minus 0.05. So plus minus 0.05, that is the actual mass. That's the interval for the actual mass. The empty container has a mass of 6 kg to the nearest 0.5 kg. So to the nearest 0.5 kg, what does that mean? The error in this is going to be plus minus 0.25, right? Half of this. So it's going to be 6 plus minus 0.25. That's the mass of this empty container. We want to find the greatest possible total mass of the container and the 100 boxes. How do we think about this? We want the greatest possible total mass. Now, if you want the greatest possible total mass, how is the mass going to be calculated? Mass is going to be of the container. There's one container, so you can say mass of the container plus 100 boxes, 100 times mass of one box. Right? That's what the total mass is going to be. We want the maximum possible value of the total mass. How is that going to be calculated? We have addition here, right? So we would want both the numbers to be individually as big as possible. We would want the mass of container to be as big as possible, and we would want the mass of box to be as big as possible as well. What does that give us? Greatest possible mass of the container and the greatest possible mass of the box. That is what is going to maximize the overall number, because there's a plus sign between them. We want these individual numbers to be as big as possible. So what's the maximum possible value of mass? We would say that's 1.5 plus 0.5. 0.05, what's that going to be? 1.55, right? We add this, and similarly, the greatest possible value. So sorry, that was supposed to be for the container first of all. That is 6 plus 0.25, that's 6.25 plus 100 times mass of one box. Greatest possible value of a box, value of the mass of a box, 1.5 plus 0.05. What does that give us? 1.55. And that is going to give us the result that becomes 6.25 plus 155. 155 plus 6, that's 161.25. And the maximum possible value of mass, that turns out to be 161.25. Okay, so that's the idea. That's how we find lower bound of something, the upper bound of something. If we have some calculation to do, we write down the formula for that first, and then we first figure out in that formula for each quantity, are we going to use the maximum value, the minimum value? It would depend on whether you have a plus sign or a minus sign or multiplication or division. Based on that, you decide whether to use the maximum possible value of each quantity or the minimum possible value of each quantity, and that gives you the overall maximum or minimum based on these rules. Okay, I hope that makes sense. Any questions? Any problems with anything? No problems? Okay. Unfortunately, we could not do a lot of questions today because I ended up having some internet issue because of which we started late. But I think we have covered the main concept and done enough practice that you should be able to do other questions like this as well now. So that's it for now. I'll see you again in the next class. Allah Hafiz.